All right, well then, since that worked out well, let's go ahead and do a poll to see how well you remember last time's stuff. So, got 3 questions here covering what we went over last time. Go ahead and put your votes in. And once everyone's voted, we will come back together and see how y'all did. All right, about another 20 seconds. Okay, so let's go ahead and go over these. Let me share these results. All right, so we look at this. Number 1, which function gives a brief summary of a variable, including the type of data and its first values? So we listed off a bunch of functions that we had last time. Looks like the number 1 answer is correct. It's str for structure. So that one will give you the type of data, integer, numeric, whatever, a little bit of information about it, like how long it is, and then what is a peek at its first values. The next best one, type of, is close, but it will just give you the type. It won't actually give you a summary of its data or its first values. And if you look here, you can see this. Let's just make a variable x, which has the values 5 to 10, using our little colon assignment, our colon operator. So we use that and we do the structure of x. Down here in the console, you can see it's an integer with 6 elements, and we can see the first ones. However, if we do type of x, then we just get it's an integer, and that's all. So structure is the one that will let you sort of peek inside the variable. Also remember that you can get that through the structure call itself, the str function call, or it's also over here in the environment panel where we have essentially a printout of the structure call here next to the variable name to help keep track of things. So that's the first one. Second one, if you create a variable of x equals c combined, true, 7.5, 1, false, and negative 45, what is the type of data that is stored in x? So the number 1 answer we have is complex, and that is incorrect. Sorry, guys. Remember, complex numbers, this goes back to algebra, are ones that include imaginary components. They are almost never used by researchers in any field I've worked with. I assume mathematicians use them, maybe engineers, but I work generally with like biologists and that sort of thing, and I've never had use for a complex number. So not that one. Number 2 is correct, numeric. So numeric or double, same one, that's decimal numbers, remember. So if we look at the values here, we've got true and false are Boolean values. So they're true, false, there's true, false, logical. 1 and negative 45 are integers, so they're whole numbers. And 7.5 is a numeric, a double, because it has a decimal point. So 7.5 is the most complex of these. That's the wrong, most complicated of these. And so everything gets forced to be that value. It force be that type, which is numeric. Let me just demonstrate that here. X equals C, true, 7.5, 1, false, negative 45. So if we run these two lines of code, we see that X is a double numeric. And if we get the structure of X, come on, it is, see here's where there's a synonym. It's type of says it's a double, structure says it's numeric. Same thing, basically. 5 elements, and you can see here that true and false got coerced to be 1 and 0 respectively, because that's what happens to logicals when you convert them to integers or to numerics. So this one is numeric. If we'd had something in quotes, it would have been a character, but you will rarely, if ever, encounter complex numbers in most people's day-to-day research. All right, last one. What is the output of this code? As.numeric, parentheses, as.logical, parentheses, 0.45. And it looks like most people got this correct. It is 1. And I'll show that right here. That's numeric, as.logical, 0.45. So if we run that, we get 1. And unpacking this, so parentheses, remember your order of operations, parentheses start from the inside and go out. So we first, and that works with functions too. So we first convert 0.5 to a logical. 0 is false. Any other number in existence is true. So 0.5 gets converted to true. Then that gets converted to numeric. True, when it's converted to a numeric value, takes the value of 1. So that's how we get 1 out. So quick review of the stuff we covered last time in terms of looking at structure, in terms of data types and coercion among those data types. So does anyone have questions on this material? Something you were confused about? Something that I may not have explained that you still don't understand why the answer is one way or another, or just anything else that might have come to mind from last time? Okay, I'll take that as a no. Feel free to speak up if anything does come up. So today we are going to talk about exploring data frames. So data frames are sort of the bread and butter of most people's analysis in R. Remember, a data frame is basically just a two-dimensional table, a data table of information. And it's what people are used to working in Excel workbooks and such. R, that's what most people end up doing their analysis in. And so being able to use and manipulate data frames is very important. And so we're going to be talking all today about that, and probably a little bit of next time too, in terms of what manipulations you can do and how you can change the data around. So starting off, we've got an exercise. I want you to load in cats.csv from last time and get its structure. So I'm going to send a link here in the chat. And I want you to download this data frame, or download this file, it's a CSV file, load it into R, and then get its structure. And when you've done that, type done to the chat so I can keep an eye on how people are doing. Now, if you reach a point where you're stuck and you can't figure out why you're stuck, go ahead and speak up, because odds are good if you're stuck, there's at least one other person who's probably also stuck. All right, by my count, I think we've got about half the people done at this point, so we'll give a little bit more time. We'll do 30 more seconds. Okay, so let's go ahead and call it there. By my count, we have about 2/3 of the people managed to get this done, at least that told me so. So I assume that some people are having some trouble. So is there someone who has gotten stuck or has not been able to do this who would like to share what step you're stuck at? Okay, well, not going to force anyone to share. So we'll walk through this. Hopefully that clears up anything that might be missing. So first off, obviously you have to download this. I assume everyone knows how to download. Um, I saved mine to the desktop. It's right here, cats.csv. So the first thing we have to do is step 1, change our working directory. There are a few ways of doing this, but the one that's most intuitive for people is you go to the Session tab, set working directory, and choose your directory. So I'm choosing my desktop. And then as RStudio does this, you'll see some text pop up here down in my console. That's the text version. If you wanted to, you could type the setwd function and the name of the directory in quotes, and that will also work. Step 2 is to load in cats.csv. And for this, let's make a variable called cats. We use our read.csv function we talked about last time, and we give it the name of the file, which is cats.csv. We're to run that, and to get its structure, and also incidentally to check to make sure everything worked right, I'm going to use the structure function to get the structure of cats. It's a data frame which has 3 observations of 3 variables. So observations are rows, variables are columns. Those variables, columns, are name, weight, and like string, and here are the values. So we have character, some characters of the names, some numeric values for the weights, and some 1s and 0s for like string, which is how we coded it. So it's loaded as an integer. Now, some of you may have gotten slightly different answers here on this first part. You may have gotten the name is a factor with 3 levels, those levels being Spook, Mister, and River. So this has to do with version differences in R. So in, R version differences. And so in R, before version 4.0, so 3.x, the default was to load strings as factors. And we talked about factors a little bit last time, and they're basically slightly more complex structures that make some statistics easier, but also make it a lot easier for your average user to mess things up. So starting in R4, the default is to load strings as strings, which in my opinion is probably the better choice for most users. And if you want to change this, you can change this by doing options as a function, strings as factors, type this right, strings as factors equals true or false. I recommend false. This means that strings will not be loaded as factors, they will be loaded as strings. And so if you have R version 3 or earlier, I would recommend just getting in the habit of running this line of code at the beginning of your analyses. And if you got the name loaded in as a factor, I would recommend running this line of code right now and then reloading the cats.csv file so that it loads as a string. It shouldn't affect anything we're doing today, but it's just a good habit to get into. So questions on that exercise? Okay, no questions. All right, so now we're going to talk about exploring data frames. So there are all sorts of different ways you can use to explore data frames, to look inside, to see part of the data, to manipulate part of the data. We're going to look at a few of them today. We are not going to look at all of them because there are many, many of them. And as with most things in R and other computer programming languages, if there's one way to do something, there's probably at least 5 ways of doing that thing, and they're all equally valid. Some of the things we'll talk about are just different ways of doing the same thing. And so you can do one way or you can do another way. It doesn't really matter. Most people have a preference of what they like, but it's good to know about them because when you go looking on the internet for help, some people may use a different way than you're used to. And so it's good to know what it is they're doing. So the first thing we're going to do is the head and tail functions. So if you have worked in Unix at all, so if you've ever worked on like a computing cluster, Sapelo is the one we have here at UGA, then you might have heard of Unix functions with these same names, head and tail, which look at the top part or the bottom part of a file. It's the same idea here in R. Head looks at the top part of a data frame, tail looks at the bottom part of a data frame. So to look at it, we do head and then the name of our data frame, which in this case is cats. And in this case, it's not too impressive. We actually get the entire data frame. That's because our data frame is small. It's only 3 lines. If we want to get just part of it, we have to specify the number of lines. So if we do a head of cats, but n equals 10, we say we want the first 10 lines. I think this is about the default. There's only 3 lines, so that's all we get. However, if we do the head of cats, n equals 2, now we only get the first 2 lines. We can do an n equals 1 as well and get just the first line. I'm actually not sure what happens if we put n as 0. There we go. We get a 0 length data frame. We see the first 0 lines of the data frame. We do get the names of the columns, but that's it. And so again, with a 3-line data frame, this is not particularly impressive. But if you have a data frame that has 10,000 lines or 1,000,000 lines, this can be really important to be able to take a look at the top or the bottom of your data frame to make sure that the data is intact. This is also especially useful because if something's going to go wrong with your data as a whole, it usually goes wrong either at the top or at the bottom. At the top, there might be extra lines, there might be comments or something that get loaded in. At the bottom, sometimes there's just extra lines of someone hit the return a few times, and so there's a bunch of blank lines that mess up the rest of your data. So the top and the bottom are usually good to check out. So head gets to the top, tail is the same thing, but for the bottom part, we do the tail of cats with just 2. We see we have the last two lines of our data frame. And you can tell this not only by comparing it to the actual cat's data frame, where we see that Mr. and River are the bottom 2. You can actually see the row names over here on the left, indicating that it's line 2 and line 3. So that's a little shortcut. You can actually control these row names. You can rename them. You can change them if you want. Most people don't have need of doing that, and so we're not going to cover that. But it is an option available to if you want. If you want to make each row have a specific name. Manipulating column names tends to be much more common as we add or subtract or change around the columns. So that's how we look at the top and the bottom of a file. We can also, or sorry, of a file, of a data frame. We can also look at its size. So there's 3 functions here that are generally what people use to get the size of a data frame. The first is nrow, which you might be able to guess from here is the number of rows. Now we get cats, the number of rows of cats is 3. Its corresponding one is ncol, so number of columns, and that is also 3. Again, we have a very boring data frame. And then you can actually get both of these things at once using the dim function. This is dimensions. So this will give you the number of rows and the number of columns, which is 3 and 3. So that is all that part is, right? That's all that is. And again, not too exciting for a 3x3 data frame. Very, very important when you have a 10,000 element data frame. Being able to check the number of rows and columns can also be extremely useful because sometimes you can switch them by accident, just by loading something in wrong or doing the wrong transformation on the data. And so just checking to make sure your data frame is the right shape can actually be very, very useful. And if you look here, we can start stacking a few of these together. So remember how we could specify with head, we want a smaller data frame. Now, let's just say we want to save that for some reason, short frame, we'll call that. This is just the top 2 lines of cats, which you can see here. We start looking at this, look at the end row of short frame. We'll get that it only has 2 rows. We could even stack these like the dimensions of the head of cats n equals 1. Probably can make a prediction what this will be. If we take just the first line of cats, we have 1 row and 3 columns. Last thing here before we get to an exercise is summarizing a data frame. This is actually very useful. This is part of the sanity checking and quality checking you'll want to do on your data very frequently. Because oftentimes you want to see just a brief summary of what your data looks like. We're going to get into plotting in a later session, but this is just numerically like, what's my mean, what's my median, what's the range? Do things look like they're supposed to in terms of allowable values? And the way you do this is with the summary function. So if I tell it to give me the summary of cats, this is what I get out. I get 3 columns for the 3 columns of our data frame. The name has a length of 3. It is a class character, mode character, which is not particularly useful. But yeah, there we go. Length 3 character, not much. Weight as a numeric value is actually more interesting because, if you remember here, the weight has 3 values, 2.1, 5, and 3.2. We get a spread of values. We get the minimum, we get the first and third quartiles, the median, the mean, and the max. And so this is really good for sanity checking. If, for example, you're taking measurements on something that is supposed to only have positive values like age or height, or if you're working on plants like I do, like the number of days until it flowers, this is a good check to see, does my average seem reasonable? Like if I'm measuring adult males, like is their average height somewhere around 5 or 6 feet? If the average comes out to be 2.5 feet, something went wrong. If it comes out to be 110, maybe I'm working in centimeters. No, that's actually still wrong. Never mind. You get the idea, though. Negative values are really important. Some people use negative values to indicate missing, but they don't always communicate that to you. And so this is a good check to see if the values are in the range and around what you think it should be. Now, like string, we have the same here. Now it's just zeros and ones. So like the first quartile and the mean don't make as much as meaning here because they're really just true false values. We just coded them as zeros and ones instead. And so for our exercise, I'm going to have you fix that. What I want you to do is change the column like string to a logical factor and get the new summary to confirm it worked and see how a logical value gets summarized. So go ahead and do this exercise, and when you've finished, type done into the chat so I can keep track. All right, we'll do 30 more seconds. Okay, so looks like most people probably managed to get this done. All right, so changing the type of a column. So if you remember, we access the column by using the $ operator. So we want cats $like string. It's perfectly okay to use RC's little help there. And we use the as.logical function. So there's this whole family of functions that's the as.whatever to convert variables among the types, to coerce things. So we're going to convert cats.like string to a logical and then save it right back to where it was before, cats $like string. Summary of cats. When we run that, we can see that like string has been converted to a logical, and then we get the count of how many are false and how many are true. And so that's just a refresher on how to update a column, but also how we get the summary of our logical values. We get the counts of how many is true and how many is false. Anyone have a question on this? Okay. Well, this is a good segue into the next step that we're going to be talking about, which is accessing individual parts of the data frame. So we just did one right now. So if we use the $ operator, we can access one of the columns inside the data frame. So cat's $name gets us the name column out. And this name column is basically a variable inside another variable. So we have the cat's variable. The $ says look inside the cat's variable for another variable named name. That's basically what we have. That's how we access a column. And so we can do things with this where we can reassign things like we just did up here, where we make a new value and then reassign it to it. We can also save this just as its own vector. So I can say x equals cat's $name. And now if I look at x is a simple variable that just has 3 values in it, Spook, Mr. River. It's now separate from the data frame. We basically made a copy of the data, but we can now manipulate that. But in the data frame itself, we can access individual parts of this column. So just like with a normal variable, we can use the brackets to look at the second value. We can do the same in the column. Cat's $name, and then we put the brackets with number 2 in. Brackets mean I want just part of this, and 2 means I want the second item. Remember, R starts counting from 1. So it means first item is 1, second is 2. And here we have just Mr., because we took just the second item out of the name column. We can also take multiple ones. Cat's $name, we can take values 2 to 3. And so this will get us the second to the third value. We can even start telling it just give us a whole bunch of stuff. So if I do cat's $name, remember our combine function that we use to put things together? We can combine a bunch of values and get out essentially a reordering, a reshuffling of this name column. So we can say I want values 3, 2, 1, 1, 2, 1, and 3. If I run this, it will take the third and the second and the first and the first and the second and the first and the third values and spit them back out here. We've now got a new set of values, which if we wanted to, we could save that to a variable. We can then manipulate that variable and so on and so forth. This is how you can extract data from a column. Importantly, if you try to get something out that's not there, you get a missing value. So if I say I want the 4th value, there is no 4th value because we only have 3 rows in our data frame. I get this NA, not applicable. That's missing data. I can continue to ask for other things. So 3, 2, 1 again. The items 3, 2, and 1 exist, and so it will give them to me. But I still got this missing value here in the middle. And so this is something to watch out for, because if you get missing data, it oftentimes means you tried to get something that did not exist. And so you need to be careful, because this can obviously cause problems to your data downstream. If you're expecting there to be data there and there's not, there will be issues, especially because R tends to treat anything that has any missing data as completely missing. When you start doing things like means and averages and such. So watch out for this. Look out for if you're trying to ask for data that does not exist. So that's how we get individual values within a column. You can actually use that same syntax to access both rows and columns. So this is called the index. So these numbers in here, if you remember, they're the index of values inside our variable or inside our column. The index is whether it's the first or the second or the third or whatever. You can access an entire data frame by index. So if I want the second row and the third column, I can give them by giving a two-part index, where I give the row first, second row, a comma, and then the column. So cats, brackets, 2, 3 means I want, in the variable cats in the data frame, I want row 2, column 3. And if I run that, I'll get false. And if we look at cats, so we can take a look at this, row 2 is right here, column 3 is like string, and I get false out. And so we can continue doing these same patterns up here, down here. We can get cats. I want the first and the third column, so I use the combine function, 1 and 3. And then I want columns 2 to 3, so I'm going to use the colon operator. Now I have rows 1 and 3, which you can double check, like I said, with the row names. And I have columns 2 and 3, the weight and the like string. So this is how you can start pulling apart little bits of your data. And so you can pull out individual columns you care about, individual rows you care about, this sort of thing. Let me see. Yeah, before we go on to the next step, I don't want to flood you with too much all at once. We're going to do an exercise. I want you to make a new data frame containing rows 2 and 3 of cats, and with the columns 1, 3, 2, 2, 1, and 3 in that order. Get the structure of that data frame. So make a new data frame, has rows 2 and 3 of cats, but also columns in order 1, 3, 2, 2, 1, and 3. And then get the structure of that data frame. When you've done so, please type done into the chat. All right, we'll go 1 more minute on this one. Okay, so let's break this down into individual steps. So we need a new data frame, so I'll call it new frame. And then we need to take out parts of cats. So we have our cats, and we want to subset part of it, so we'll use the brackets. We want rows 2 and 3. So there's a few different ways we can do this. I'm going to use the colon operator, so 2 through 3 here. You could also use the combine function of 2 and 3 that way. Both of those are equally valid. They both work. Let's go back to 2 to 3. Then we need the columns. So here we definitely need the combine function. We want numbers 1, 3, 2, 2, 1, and 3 in that order. And so if we run that, we'll get our new frame out, which has rows 2 and 3, and then these columns. And you'll notice that it's appended little stuff to the end of our duplicate columns just to keep the names unique. And then we want the structure, which is the str command. Structure of our new frame is a data frame's 2 observations, 2 rows of 6 variables, columns. We have our name, our like string, our weight 1, our name 1, our like string 1. And so this is how we get our new data frame out. So this is a toy example of just taking a simple data frame and manipulating it. You can imagine though, if you want to subset out parts of your data where you have a massive data set and you want to pull out just the males or just everything that has a value above 50 or things, sorry, we'll get to the values above 50 in a moment. Sorry about that. But just the males, if you want to pull out just the weight, if you have like weight and age and sex and stuff, you just want those, you can pull them out. This lets you subset out your data to what you want. Are there questions on this? All right, so when you save values from a different rows in a data set, does it save it in R as a data frame? And are the values from the same columns saved as vectors? So let's see. So I'm not sure I completely understand the question, Reagan, so correct me if I'm wrong. So when you pull out data like this, you say you have these 2 rows and these columns, this becomes, this action here, this cats and the subset actually creates a new data frame. Now, if that's all I do, I'm going to just copy and paste that here. That data frame gets corrected and gets created and made. It's not saved anywhere, so R just prints it to the screen and then it's gone. It vanishes into the ether, you can't get it back. In order to manipulate it, you have to save it to a variable, in which case this variable is now a new data frame. It's not some weird look at the cats one where they're still somehow connected. They're different. So for example, if I take this new frame and let's say new frame, let's turn like string to a character. Like string. So if I run that and I look at the structure of new frame and the structure of cats, cats, our like string is still logical. it's still what it used to be. In the new frame, that's what we adjusted. That's now become a character. So essentially, when you make a copy of the data like this, the original is untouched. And this is actually very useful. Usually you want, when you load in your raw data, by and large, you want to not really mess with that raw data. You make copies of it that you can then manipulate and change, whereas your raw data stays set and pristine so you don't risk messing it up. And then you can just keep pulling things out of it as you need it. Meanwhile, second question, are values from the same column saved as vectors? So what I think that means, what you think you're asking is if these new columns that we made become vectors, they're their own vectors. Like I said, you can change one without changing the others, but each one of these columns is its own vector. Yes. Oh, okay. This is a question from the earlier exercise. So these things become their own vectors. They are separate from each other. Let me go back to the previous exercise. Are values from the same column saved as vectors? So I think I could just cover that. It says yes. Okay, yes, I did answer the question. Yes, each column is basically its own vector, which is why everything in the column has to be the same data type. You can't mix data types. You can't have in a column, row 1 is a character and row 3 is a numeric. It doesn't work. Everything in the column must be the same data type. All right, that seems to have answered the questions. So now, few last things on accessing data frames like this. Accessing an entire row or column. Because sometimes you don't want to pull out a little bit of row and a little bit of column. Sometimes you want all the rows and just some of the columns, or vice versa. Some of the rows, but all of the columns. So if you want an entire, you want all the rows or columns, just leave it blank. So in this case, if we have cats and we have our brackets, let's say we want all rows of data, but we only want the second column. So the row spot you leave blank. It's just blank, comma, 2. Our interpreter is saying, oh, there's nothing here. That means you want everything, but you only want the second column. And we run this, we see that we get all rows, but just the second column. Second column is the weight, and so we get the 3 weight values. We can also do this the other direction. We want, say, just row 2, but we want all the columns. We run this. This is row 2, but we get all the columns of the data frame. So that's just a quick shortcut. Other thing is accessing by column name. So we've already covered this a little bit. We can access an individual column using cat's $name. If you want to, an equal way of doing this is using that name as the column instead of a number. So cat's bracket comma name is the exact same thing as cat's $name. Now this is not nearly as intuitive, so people don't use this as much when you want just one column. The power comes from this in that it lets you get more than one column at once. So just as in the exercise, we could say we want columns 1, 3, 2, 2, 1, and 3. We can set up that we want multiple columns. We use our combine function again to make a single thing there. We want the name, we want the weight, we want likes string, and let's say we want the name again for some reason. Now we're asking for 4 columns by name and all the rows. And this lets us pull out a new data frame that looks like this, where we've got all the rows, because we didn't supply anything there, and then we have the name, the weight, like string, and then the name again. So this lets us get multiple columns by name, which is a very useful feature, because oftentimes this is much more readable. Like if I said I want columns 3, 2, 1, and 3, that's really hard for someone reading your code to understand what it is you're talking about. But if you use their names, you say, I want their names, their weights, and if they like string, someone reading your code can understand what it is you're doing. And this makes it much easier to track what exactly is going on in your code and what you're trying to do to your data. The last thing we're going to talk about this way of accessing is, again, a way of making your code a little bit easier, a little bit more robust, and that's using variables to access rows and columns. So up here, all the things we've been doing so far, we've just been plugging the numbers or the names directly in. But you can actually use a variable in place here. And this I find very useful because this helps keep your code a little cleaner and it makes it a little easier to understand. So let's say I want my new rows to be rows, we use my combined 1, 3, and 2. 1, 3, and 2. And my new columns to be name and weight. Now I can access cats using my new rows, comma, new columns, new calls. So here, instead of giving the numbers directly or giving the names directly, I have saved those values to variables, and I can use those variables as the index. And when I run this, R handles it perfectly fine. It sees new rows, it looks it up in its memory, says, oh, new rows is the values 1, 3, and 2. New calls is the character strings, name, and weight. And so it plugs those in, and it gets out the data frame that I want here. This can be very useful for making your code readable. You can say, these are the new rows I want. These are the new columns I want. And then you can see here, this call, getting the new rows, new columns, is not only shorter and easier to read, it's more intuitive than a longer call like this one up here, where I've put a lot of parentheses and quotes and everything all in a single line. This helps break apart what you're doing, which makes it easier to read and easier to understand. And again, most of the time, the person you need to do this for is yourself when you come back to it 2 weeks or 2 months later and you have no clue what you were doing at the time. This makes it very easy to get back in and understand what's going on. So, time for an exercise. Using variables to index cats. I swear I can type. Make a new data frame that has the rows 2 and 3 and the columns in order of weight, name, and like string. Then summarize that data frame. All right, go ahead and take this, use variables to subset and create a new data frame. And once you have that, summarize that data frame. When you are done, go ahead and type done into the chat. All right, I'll give you all 1 more minute and then we've got to move on. All right, 10 seconds. Okay, seems like the further we go in this lesson, the fewer and fewer people are managing to finish the exercises. Am I going too fast? Are people having trouble? Well, I guess that's a no. So, all right, well, we'll go on then. So, doing this exercise using variables. So, just our new rows. We want to make a new data frame that has rows 2 to 3. So, I'm going to use the combine function to make a variable that has the values 2 and 3 in it. And also use the combine function to make a variable that has the names of the columns we want in order, which is weight, name, and likes string. Then our new cats is our cats data frame, but we want our new rows and our new columns being what we take out. And then we need to summarize that. So we take the summary of new cats. We take all this and run it. Just showing here, so our new cats has just these 2 rows, rows 2 and 3. It has the weight, name, and like string that we want. And summarizing it, we get, I mean, we've seen this before. The weight, the values are slightly different because we have a smaller data frame, their name, and our like string summary. So that's how we can use variables to start subsetting data and pulling different things out. Again, very useful if you have, say, certain columns of data you want or certain rows you want. Questions? Okay, so lastly, we're going to be subsetting data with the subset function. Now, this is probably the single most useful one because everything we've done here has been selecting out things where we know which ones we want. We know we want row 2. We know we want the column called name or column 3 or whatever. Subset is useful because instead of choosing specific columns or specific rows, you get to filter your data frame based on the values it contains. And so the way we do this is we use the subset function. We tell it what we want to subset, in this case, cats. So our first argument here is our data frame. There's a comma. And then we need to tell it how to choose what to keep. And so this will take the form of something like cats $weight is greater than 3. Now we're going to talk about the second part for a while because it's an important thing to understand. First, I'll run it to show you what happens. So here, we've run subset on cats, picking out only the ones where the weight is greater than 3. And you can see that's exactly what we got. We got rows 2 and 3, which are the 2 where the weight is above 3. Poor Spook, apparently, is a lightweight at 2.1 kilograms. And so he did not make the cut when we were making this filter. Now, this second part here is extremely important. This tells R which ones you want. And for this, to understand how this works, we're going to talk about comparison operators. So as we mentioned, operators are little symbols that do things. So we have the assignment operator, which is the equal sign. We have the colon operator, which makes a range of integers. Comparison operators compare things, and there are 6 of them. So that is greater than, and then the left-hand little caret is less than. These you should recognize from algebra. They're just the standard mathematical symbols: greater than, less than, fine as normal. Now, the next thing related to these is greater than or equal to and less than or equal to. Now in math, we have a special symbol that is the greater than symbol with a little line underneath it, or the less than symbol with a line underneath it. That's nowhere on our keyboard. And so programming languages take a shortcut and they just combine 2 symbols. So greater than or equal to is just the greater than sign immediately followed by the equal sign. And so you can probably guess less than or equal to is the exact same thing. And what these do is that they will compare the things on the left and the right-hand side of themselves, and they will figure out if this comparison is true or not. You can see here is 5 greater than 3. If we run that, R returns true. 5 is greater than 3. So we say 5 less than 3, R returns false. 5 is not greater than 3. And same thing with greater than or equal to, less than or equal to. R is evaluating this and returning a logical value of simply true or false. We can also test things of equality. So equals equals means is equal to. Same thing. Now, we've already dealt with the 1 equal sign, which is the assignment operator. This is not the same. And in fact, if you try to make a comparison with a 1 equal sign instead of a 2, your code will mess up, guaranteed, because R will try to assign something. But 2 equal sign means these things are equal. So 5 equals 5 is true. 5 equals 5.0 is also true. And then the opposite of is equal to is not equal to, which is exclamation point equal sign. This exclamation point is just how you say not in most computer languages. So 2 equal sign is equal, exclamation point equal sign is not equal to. So 5 does not equal 5 is false. And so that's what these comparison operators are doing. The key point up here in subset is that when you give R a variable with one of these, and that variable, when you give R a variable or just some sort of value, it evaluates it for every value in that vector, in that variable. So if you remember, cat's $weight is a vector, it's a column, so it has 3 values. And so this greater than 3 gets evaluated for every one of those. Put that in here. You can see that it gives me 3 logical values out: false, true, true. And if you remember, that's because cat's $weight, 2.1 is not greater than 3, so that's false. 5 is greater than 3, so true. 3.2 is greater than 3, that's true. And this sequence of false and true is what R uses to determine which rows it keeps. The rows where this function, where this expression evaluates to false, gets dropped. The rows where it evaluates to true gets kept. And that's how you subset out rows of your data frame. So we can do this in other ways. We can subset cats so that cat's $name equals spook. And so now we have only the rows where the name is equal to spook. Or we can say it's the names that are not equal to spook. And now we have that. And so this is, again, useful for subsetting your data out. If you say you want only the males, or you want only the plants whose height is above 2 meters, or only the mice that are positive for a certain genetic mutation, you can subset data out this way by using the subset function and giving it one of these expressions to evaluate. The one other thing I'm going to say here is that occasionally it's useful to simply negate one of these. Now, honestly, most of the time you don't need to because you already have an opposite. The opposite of greater than is less than or equal to. The opposite of greater than or equal to is less than. The opposite of is equal to is not equal to, etc. So usually the operators themselves are all you need. But sometimes it's a little clearer if you just say, I want the opposite of this expression. And to do that, you can simply preface the entire thing with an exclamation point. That's not. And so this will take this expression. I'm going to highlight it right here and show what happens. So if I highlight just this part of code, it will run only that part. Oops, not cats greater than 5, cats $weight greater than 5. There we go. So cats $weight greater than 5 is false, false, false. None of them are greater than 5. However, if I include the exclamation point now, it negates all that. It flips all of them. Every true becomes false, every false becomes true. And so now we have true, true, true instead. This is not common that you use this, but every now and then it's actually easier to, to specify it this way. And so to wrap up, we're going to do an exercise. Subset out the cat's data, keeping only the, the ones that do not like string. And when you've done this, type done into the chat, please. We'll do another 30 seconds. Okay, so as with many things in R, there's more than one way you could have done this. So my hope is that you use the subset function. So that's what I'm going to focus on. So we're going to subset cats. And then this expression could be of one of several things. We have cats $like string equals equals false. That's one way of doing it. Saying we want all the ones where like string is equal to false. There's another way we could do it too. I'm going to copy this. We could say cats like string does not equal true. That's another way of doing it. This will work out to be the exact same. If I run these 2 bits of code, you'll see that the Boolean vector that comes out is identical. There's also another way we could have done this. So let me paste this again. So remember how I said that this expression here evaluates to a Boolean vector. That's what R is expecting here in the subset function. If you remember, like string itself is actually a Boolean vector. It's a series of trues and falses. So in this specific case, we could even shortcut it and say, I want the cats that do not like string. So cats.likestring gives me true if they like it, false if they don't. And so I use that exclamation point to negate that. Say, I want the cats that do not like string. And there we have, again, the exact same thing coming out. You can use this trick with other values, like with weights and stuff, but remember, they all get evaluated as either true and false. So I wouldn't recommend it because it's doing something weird where you're saying, okay, anything that's 0 will be false and anything that's not 0 will be true. I don't recommend doing that. But if you have a column that is just trues and falses already, you can use it directly as a filter like this. The thing is, all 3 of these are equally valid. There's nothing better or worse than any of them. It's just a matter of which one is the clearest for you, which one makes the most sense and is the easiest for others to read. So that's where we're going to stop today. Next week, I will not be teaching. I will be here participating, but Davis Gamodi, who's been our helper today, will actually be the instructor. He'll continue on with more of this and move on into some conditionals where we test things one way or another. So before we close up, are there any questions from anyone? Okay, can we rename the new columns in a new data frame? So this is line 65. So new frame equals this. So I'll copy this down here. The answer is yes, although you probably would not want to use this particular syntax to do that. Instead, because this will create our new data frame and it has those weird names in it and everything. So it is possible to adjust these. I don't want to get into a long tangent of the so-called proper way of doing this because it involves new functions and stuff that I think would probably confuse people more than would help. So with what we've talked about, the easiest way of doing this is rather than try to use this, let's admit it, kind of convoluted way of copying columns over, let's make a new column like we demonstrated last time, where if we have, let's say, new frame equals cats. There we have our data frame. And if we look at new frame, then we see that it is just an exact copy of cats. But now we can start making new columns to it. We can say new frame $, new name equals cats $name. Now this creates a new column in the data frame and assigns it the values in cats $name. And so if we look at the structure of this, we get that it now has an additional column that has the same stuff in it, but with a more intuitive name. And this is what I would recommend you do if you need to create a bunch of new columns in a data frame that are similar or identical to other ones, is use the $ operator, because that way you can specify the name right away. You don't have to worry about changing the name later. And it's usually much clearer to read because you're doing in a single line of code what would take 2 or 3 lines of code to copy it over and then figure out which column you need to rename and then change the name of that column, which can get kind of convoluted and confusing. So I'd recommend if you need to copy a column over, you use this syntax instead. You use a $ to create a new column and just assign it the new values. Is that clear? Any other questions? Okay, so that's going to be the end of our instruction for today. I'll send out link to the video and to the original notes tomorrow. I'm also going to be sending out a homework assignment. So a lot of what we've been doing here has been little toy examples, things that are to show you how stuff works. But let's admit it, this is kind of far removed from most people's actual data analysis. So what I'm going to be sending out is a link to an actual data set that contains many hundreds or thousands of lines of data, and some assignment in terms of what to do with that. Some of it's very simple, very specific commands I want you to run. Others of it is more general, like compare this thing with that thing and tell me which one, or tell me how they compare, which is a more research-like question. And so the point of it is to give you more realistic data set and have you start translating all these little bits and pieces and tools we've been talking about into how you can unpack a question and figure out how you arrange those tools together to get the answer you need. So that will be going out sometime tomorrow. In the meantime, thank you all very much, and I will see you next week. Take care.